Okay, welcome to Chapter 1, Section 2. We're going to be talking about some vocabulary and some abbreviations. First up, chemistry deals with matter. And what is matter? Matter is stuff. It's anything that has two properties. It has mass and it takes up space. It's volume. And when you look at those definitions, mass is the amount of matter in an object, which is not really a great definition. Matter has mass. Mass is the amount of matter. Not awesome. So let's instead go with mass as a measure of inertia. Inertia is the physical property where, how hard you have to push on something in order to get it to change velocity. If it's moving, velocity is, speed and direction. So if you want something to change how it's moving, you have to push on it. And the more mass it has, the harder you have to push in order to get that change to happen. So that might be one way of thinking about mass. For volume, there you're getting into really, really, really deep philosophy sorts of stuff. You're talking about how much space something takes up and what is space. It's, it's hard to come up with a decent definition, or at least I haven't really come up with one yet. Nevertheless, matter has mass and it takes up space. Space being, the stuff all around us. And there's really not any way to get around that. So we'll just leave it at that, perhaps. Yeah, well, let's go ahead and leave it at that. Now, matter comes in different phases. Okay, the phases of matter. Okay. These correspond more or less to the ancient elements. Not the modern elements in chemistry, but the ancient elements, earth, water, wind, and fire, right? Okay, so you have solid. That is, ancient earth. Okay, so solid has a definite form, or let's see, it's a definite shape and a definite volume. Solids are the stuff that don't change shape. You push on them and they push back. In physics terms, they resist shear forces. If you push on them, then they will retain their shape. Whereas the other forms of matter, you push on them, they don't retain their shape. They can't push back. They can't resist those shearing forces. Okay. Next up, we have our liquid, aka the ancient element of water, which has no shape, but it does have a definite volume. You pour water into a container, or a liquid, I should say, into a container. It will take on the shape of its container, but it has a set volume. The volume doesn't change. This is because, for both solids and liquids, the particles that make up the solids and liquids are touching. And this here is my abbreviation for particles, PTCLS. A particle is just any small object, a tiny thing. Could be an atom, could be a molecule, could be an electron. It's just any tiny bit of matter. So the particles of solids and liquids are touching. Okay, you look at the space in between any two particles. There's going to be another particle there. Okay? The particles are all touching one another, all butting up against one another. That's why they have definite volume. But for solids, the particles are locked in place. Okay? They can't move. They are sitting in. It might be a rigid arrangement of a three-dimensional pattern. If it's a crystalline solid, if it's an amorphous solid, then there's no pattern, but they're still locked in place. The particles can't move. But for a liquid, particles are free to move. Okay, the particles are constantly slipping past one another. And that's why it doesn't have the definite shape. That's why it can't resist the shearing forces. They're not locked in place. You push on them, the particles will budge out of the way. And finally, we have air, or gas. Has no shape, no volume. Okay. When you put gas into a container, it will take on the shape of its container and it will expand to fill the container. Gases have neither shape nor volume. Okay, for gases, particles are not touching. The particles are separated by very, very large distances. Okay, so here's one particle of gas, here's another particle of gas, and there's a huge gap in between them. Like 1,000 times the radius of the particles of the gas. The space in between them is much bigger than the individual particles themselves. So it definitely can't resist shearing forces. It can't resist any force you apply to it. And it has no shape. You'll notice that I have left out one of the classical elements, okay, because everything went wrong when the Fire Nation attacked. Okay, this is actually, let's see, I should keep this similar to how I had it before. Plasma, which would be fire. Okay. Plasma is a gas that has been heated really, really hot. It's so hot that electrons are being stripped off of some or all of the particles in the gas. So you end up with a gas that's full of ions. Ions are charged particles. So instead of being electrically neutral, they have a positive or a negative charge. So that's a plasma. That's what fire or flame technically is it's a really hot gas, so hot that it's stripped off some of those ions, and that's why it glows. Plasmas have really, really strange behaviors and properties. Now, those aren't the only phases of matter. You also get, say, like neutron stars, where gravity's become so intense that you have nothing but neutrons. The electrons have all been squished into the nucleus. So it's just a degenerate form of neutron matter. And things like that, or the interior of black holes and other weird forms of matter. Suffice it to say, we are never going to encounter a black hole in our labs, so you don't really have to think about that. We're also not even really going to deal with plasmas. I just wanted to round out the 4 classical elements. But solids, liquids, and gases. So shape, volume, and we have solid, liquid, and gas. And there you go. Solids have a definite shape and a definite volume. Liquids have a definite volume but no shape. And gases have neither shape nor volume. And while we're talking about matter, let's go ahead and get this guy out of the way. Mass versus weight. These are not the same thing. Okay? Mass is the amount of matter inside of an object. Weight is gravitational force. So these two are related, okay, because the gravitational force is determined by the mass, but they're not the same thing. The mass is actually the measure of matter, okay, and it's measured in grams or kilograms. Weight is a measure of force, so it's going to be measured in newtons, the unit of force. You break that down into its basic units. That's kilograms, meters per second squared. So you can see it's related to mass, but because it's got kilograms in it, right there. But it's not mass. We can measure mass, we can measure mass by measuring weight, because the force of gravity is equal to the mass of the object times the acceleration due to gravity, which is a constant here at the surface of the Earth. Negative 9.81 meters per second squared. So if you measure the weight of the object, the force of gravity, and you know the gravitational acceleration, which we do, we've measured it fairly well, then you can get the mass out of that. And that's technically how scales and balances work. They're doing the conversion for you. But be aware, they are different things. Mass is constant. It doesn't change no matter where you go. An object has as much matter as it has, but the force of gravity is going to change because the force of gravity depends upon the mass of other objects. Okay? So that's mass versus weight. Needed to get that out of the way. Needed to be said. Okay, so mass, weight. And next up, let's go ahead and talk about the laws of conservation. Okay. Conservation, okay, so means, something is conserved, means it doesn't disappear. Okay. So if something is conserved in science, that means that you don't have anything magically appearing, you don't have anything magically disappearing. If something is conserved, then the quantity is constant. Whatever you have at the end, you have at the beginning, okay, and vice versa. Okay, nothing is lost, nothing is gained. So things that are conserved are things like energy. Okay, the energy of the universe is constant. So the energy of a system is either constant or it can only lose or gain energy from the outside. Nothing magically appears or disappears. Similarly, matter is also conserved. Physical things don't just appear or disappear from nowhere. They have to come from somewhere. And finally, charge is conserved. Okay, charge meaning, negative charge or positive charge or neutral charge. Okay, the charge that you have at the beginning of a process is the charge you're going to have at the end of the process. Total charge doesn't change. There are other things that are conserved, like you'll hear talk about conservation of momentum, stuff like that. But these are the three that I really want to focus on for chemistry. Energy, matter, and charge. Those three will always be conserved, and you will always end with what you started with. Next up, let's talk about our particles. Okay, I've been talking about particles a lot. Let's talk about some of those particles. We have, for example, subatomic particles. Those are going to be your electrons, your protons, and your neutrons. And those are how I tend to write those, just because it's a lot faster and it saves space. E- for electron, P+ for proton, N0 for neutron. Okay, and subatomic particles go together to make atoms. Atoms are the smallest unit of chemistry, the smallest particle of an element that has the properties, the chemical properties of the element. Okay. So one of the chemical properties of iron is that it reacts with oxygen to make, rust. and a single atom of iron will react with oxygen. But the physical properties of iron are different. The physical properties of iron include melting and boiling, and it's kind of nonsensical to talk about melting and boiling when you're talking about a single particle. If you only have one atom, is it a solid, a liquid, a gas? Okay, some things are only formed in association with other particles. So an atom is just made up of subatomic particles, but it's the smallest unit of an element that has the chemical properties of the element. Atoms go together to make up molecules. Okay, that's two or more atoms that are chemically, that's important, they have to be chemically bound together. And the nature of chemical bonds, chemical bonds are, let's see, sharing, or the bond is sharing or exchanging electrons. We'll definitely be going into that more later. Just know that molecules are two or more atoms that are chemically bound together. Now there's something that we need to talk about that is going to cause a lot of difficulty and a lot of confusion. Namely, the diatomic elements. And a few others that are not diatomic, but that are similar, that are related. Okay, di means two, so we're talking about elements that have two atoms. Meaning, in nature, the diatomic elements are found as molecules with two atoms. And the diatomic elements, I always remember them. You may come up with your own method for remembering them, but they are these guys. Brinkelhoff. Okay, that's the elements bromine, iodine, nitrogen, chlorine. It bugs me unreasonably that I can't put the H in chlorine. Hydrogen, oxygen, and I almost misspelled it. Fluorine. Okay. If you look at a periodic table, you'll notice that these guys are all over on the right. The right-hand side of the periodic table, that is. Well, with this sort of exception of hydrogen. Hydrogen is over here on the left. But sometimes you'll notice on periodic tables they have it over here on the right next to helium. As they have it in both places, I should say. Sometimes they have it on both places. But here, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So these are your diatomic elements, the 6 and hydrogen. In nature, they're always found as a pair of atoms bound together. So it's always bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So when I talk about those elements, I will always be talking about molecules, okay, the molecular form. The only time we're not talking about the molecules, when we're talking about atoms, is either when we're talking about them being bound to something else, or when we actually say atomic, whatever, say atomic oxygen. Okay, in that case, we're talking about a single atom of oxygen. So the way we write molecules and so on, we have the number of atoms written in as subscripts. So when you're talking about these elements, these diatomic elements, you always have to have the number 2 written next to the letter. If you just have the name, obviously you're not going to have the number 2, but you can sort of assume that it's there. Now, other elements are also not atomic. Those elements are also nonmetals. We'll get more into that later. But for example, you have carbon. Carbon has two allotropes. Okay, an allotrope is just an elemental form. So one allotrope of carbon is graphite. Yes, the stuff in your pencils is pure carbon. Well, not necessarily pure, but fairly pure carbon. And the other one is diamond. Okay. In graphite, what you have is carbon atoms bound together in these rings, with each carbon atom being bound to three other carbon atoms. Okay, so they make these sheets, these two-dimensional sheets with these six-membered rings, with each carbon being bound to three other carbons. Okay, so graphite is the two-dimensional form. The other one is carbon, and this will almost certainly fail, but I'm going to try. So carbon, 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 carbon. It forms a three-dimensional structure in which each carbon atom is bound to four other carbon atoms. And like I said, it makes a sort of three-dimensional structure. It's hard to draw in 3 dimensions. It's hard to draw anything in 3 dimensions. It's hard to draw a 3-dimensional array. But just take my word for it. Diamond is the 3-dimensional form. We very, very rarely deal with diamond because graphite is more stable at room temperature. That's why diamonds are expensive. But they say diamonds are forever because, it wants to be graphite, but the reaction is very, very slow. So it'll stay diamond for a good long time. It's a good investment. That's what I'm trying to say. But my main reason for bringing this up is that it helps us throw in the word allotropes there. Okay. Other elements that are not simple atoms are sulfur. Okay. Sulfur, it's a very pretty element. It's bright yellow. It comes as S8, an 8-member ring. It's sulfur, 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 sulfur. Okay, so it's got 8 sulfurs in a ring there. I have a nice story about sulfur if you ever want to hear it. Well, it's not really a nice story. I think it's just a fun story. Anyway, so this is an actual molecule of sulfur. Okay, those rings are discrete, whereas carbon, those sheets of graphite and the 3D structures of diamond can be as big as you want. This is all there is to a molecule of sulfur, is just that 8-membered ring. Next up, you have phosphorus, is another element that is not simply an atom. Phosphorus, it comes in a lot of elemental forms. Has several different allotropes. There's black phosphorus, white phosphorus, red phosphorus, violet phosphorus, and so on. This is the only one I really want to talk about. That's white phosphorus. It is incredibly reactive, incredibly toxic. Just P4. It's 4 phosphorus atoms bound together in a sort of pyramid. And that's really all I want to say about that. So what you'll notice for these is that all of these non-atomic guys are over here on the right-hand side of the periodic table. There's almost certainly, I've ignored selenium, I haven't talked about it. I could in the future. Go away. Okay, is selenium. I don't know the elemental form of selenium. I have never ever dealt with selenium. But that said, the only ones of these I expect you to know are Brinkelhoff. Okay, these guys at the top right, and of course hydrogen hiding over here on the left. So definitely, always remember Brinkelhoff. And let's go ahead and wrap up this section by talking about substances. I may have mentioned substances a few times. It's another term. It just means, stuff. For when you don't want to talk too specifically about what kind of matter you're talking about. Substances come in different varieties. Not all substances are the same. So first off, you have your pure substances. Okay, so a pure substance is going to be either an element or a compound. So a pure substance, it's only one material. Okay, all of the stuff in a pure substance is the same chemically. Okay, chemically uniform. Okay. So a compound can be broken down chemically. Okay, so you can take a compound, you can break it down chemically. You put in energy. You can fire electricity through it, or you can subject it to heat or flame or something. But you put energy into it, and you can break apart the substances. You can break it apart into new substances. Is what I'm trying to say. You can break it apart often, not always into elements or into smaller compounds. So what we're talking about here is molecules. Sort of. I'll explain later how not everything is molecules. But whereas an element, no breaky. Okay, you cannot break it down chemically. But pure substances, whether they are compounds or elements, they are chemically uniform. Okay, everything in there is going to have the same chemical properties, and you can't break it down physically. Okay, you can't go in with your hands to separate the things. You can't, boil off part of it or melt part of it or anything like that. Okay, it can only be separated chemically. Elements, you can't even do that. Next up, you have your impure substances, but that's not a good way to define them or describe them, so we call them mixtures. A mixture contains two or more pure substances. Okay, so it's going to have two or more elements or two or more compounds, and it can be broken down or separated physically. Okay. So a mixture can be separated physically. You don't have to use chemical means to separate it. That said, they do come in two different varieties. You can have a homogeneous mixture or a heterogeneous mixture. Okay. So a homogeneous mixture is uniform. Okay. The different parts of a homogeneous mixture look the same. Okay. Okay. Same physical properties throughout. Okay. So, for example, a solution. Okay, homogeneous mixtures are often called solutions. Okay, so salt water. Okay, salt water or Windex, those are uniform in appearance throughout the entire thing. So those are homogeneous solutions. Heterogeneous solutions are not uniform. Okay, you look at one spot in the mixture, it'll look different from another spot in the mixture. So a pile of rocks would be heterogeneous, or a salad would be heterogeneous. It's a bunch of stuff jumbled together, but it's not uniform. Okay, you could pick it apart by hand is another way of doing it. Another way of saying it. By hand. Not by hand. Okay, they can be separated physically, both of them. Okay, you could separate salt from water by boiling off the water, for example. But you can't just pick it apart with tweezers like you could a salad. For example, I always pick the tomatoes out of my salad because I don't like raw tomato. All right, so that gives us a sort of hierarchy. You can have a whole lot of different kinds of substances, but they can be pure, or they can be mixtures. So pure means chemically uniform. Mixtures are not chemically uniform. The different parts of the mixture will have different chemical properties. So when you look at salt water, the salt has different chemical properties from the water. All right, so for a pure substance, they can be an element or it can be a compound. And the difference there is that a compound can be broken down chemically into two or more substances. Okay. So an element cannot be broken down chemically. It is a single substance. There is no other kind of substance there. A compound, it is chemically uniform, but you can break it apart chemically into two or more substances. Okay. Those substances that you break it apart, they might be compounds, they might be elements. Okay. So for example, CO2 can be broken apart into carbon and oxygen, two different elements. Okay. But calcium carbonate, chalk, you can break that apart into calcium oxide and carbon dioxide, two different compounds. Okay. But each of those is still, a substance. And the mixtures are, of course, homogeneous and heterogeneous. And this means just that the homogeneous mixture is physically uniform, the heterogeneous is not physically uniform. So those are the four different kinds of substances. And one last thing to note, another difference between pure and the mixtures is that the composition of a pure substance is constant. Pure oxygen is always pure oxygen. Pure carbon dioxide is always going to be, 1 part carbon to 2 parts oxygen, and so on. Okay, you cannot alter the composition of a pure substance. But for a mixture, the composition is variable. Okay, you have a liter of water. You throw in a tablespoon of salt. You have salt water. You throw in 10 more tablespoons of salt. You still have salt water. Okay, the composition is variable. It can change from mixture to mixture. Okay. So that's another difference between the pure and the impure substances. And that does it for this lecture. So let's go ahead and leave it there.